In this video, we'll take another look at an example where we're finding horizontal and vertical tangents to some polar curve or some polar function. Here I have r of theta equals 2 times 1 minus cosine theta, where theta is between 0 and 2 pi. 2 pi is not inclusive there. Okay, so what I want to look at are to try to find the derivative and have that determine whether I have horizontal or vertical tangents. And what I need you to recall is that the derivative dy dx is found by dy d theta divided by dx d theta. Okay, and when we set this equal to 0, we're finding horizontal tangents, right? That's the same as it has been for a while. Set it equal to 0, we get horizontal tangents. And when a fraction is 0, that's the same as saying the numerator is 0. Okay, when we set the denominator equal to 0, that's when we're really finding undefined slopes, right? Undefined tangents are vertical tangents. Okay, when the slope is undefined. And for us, that's when dx d theta is equal to 0. So what I want to do now is figure out what x and y are in terms of theta, right? I have r. I need x and y in terms of theta, and then I need their derivatives, and to set them both equal to 0. So first what we'll do is we'll look back at our function here, and I want to write down x as it corresponds to theta. So for us, we remember that x of theta is r of theta times cosine theta, or r cosine theta. R is my given function. That's 2 times 1 minus cosine theta, and I just plug that into my x, right? So there's my x of theta, and I want its derivative with respect to theta. And what I notice here is that I really have two functions of theta multiplied by one another. When I take a derivative, I need the product rule. So I go through, I find dx d theta, product rule, leave the 2 out. I get 1 minus cosine theta first times derivative of the second is minus sine theta, plus cosine theta times derivative of the first is 0 plus sine theta. Okay, I want to eventually set this equal to 0 and solve, so I'm going to try to combine like terms as much as I can and then factor. Okay, so distribute everything. I get 2 times 1 minus sine theta plus sine theta cosine theta plus another one of the same, sine theta cosine theta. Combining sine theta and cosine theta, I get 2 of those minus sine theta, and I set this equal to 0. I notice that sine of theta is a like term there. I'm going to factor that out, because if I can factor that out, then I can solve it a little bit easier. And remember, when I set dx d theta equal to 0, I get vertical tangents. Okay, vertical tangents. Factoring that equation or that expression on the left-hand side of 0 there, I'll be able to set each factor equal to 0. So let's recopy that down. I have 2 sine theta times 2 cosine theta minus 1, all equal to 0. And I'll set each of those underlined expressions there equal to 0. First, 2 sine theta equals 0. Well, that happens when theta is 0 and pi, right? The next is when 2 cosine theta minus 1 equals 0, or when cosine theta is equal to 1/2. And for this, I try to remember when cosine is positive, and that's in the first and fourth quadrants, right? So theta there has to be in the first quadrant and the fourth quadrant to give cosine a positive 1/2 value, okay? And if we remember, cosine is 1/2 at our 60-degree angle, or pi over 3. In the first quadrant, that's pi over 3, and in the fourth, that's 5 pi over 3. So all 4 of those angles should give me a vertical tangent line. Okay, what I want to do is I want to find the corresponding r value using my equation. R of theta is 2 times 1 minus cosine theta. So for each of these thetas, I'm going to plug them in to my r there, r of theta, and find r, so I can plot these points. I can see what they look like on a graph. I can see where these vertical tangent lines are. Okay, and I'm looking for the polar points here. So plug in theta is 0, r of 0 is 2 times 1 minus cosine of 0 is 1. So 1 minus 1 is 0, times 2 is 0. that point corresponds to r theta being 0, 0. Okay? Do the same thing for pi. Plug in pi for r. 2 times 1 minus cosine of pi is a minus 1. Minus 1 minus negative 1, sorry, is a 2 times 2 is going to give me a 4, and the angle is pi there. Again, remember these are in the form of r comma theta, the radial distance from the origin, and then the angle counterclockwise from the polar axis. And the last two I'll go through rather quickly. When I plug in pi over 3 to my function there, I get a corresponding r of 1. And when I plug in 5 pi over 3, I in fact get the same thing because cosine of theta is the same at pi over 3 and 5 pi over 3. So I get the point 1, 5 pi over 3. These 4 points will be the points of vertical tangency, right? The places where I have vertical tangent lines. And I'll plot them in just a bit, but first I'm going to go through and find where my tangent lines would be horizontal instead of vertical. So again, vertical, we did dx d theta. Vertical, we'll do dy d theta. We have to remember that y is equal to r sine theta for our polar coordinate conversion, right? So r sine theta, we know that r is 2 times 1 minus cosine theta. So when I plug that in, again, I have a product when I go to take a derivative with respect to theta. Here I'm taking derivative of y now. That's my y coordinate. So when I go through, I do product rule again, but this is slightly different, right? Instead of a cosine with the double underline there, I now have a sine. So this will come out a little differently. Leave the 2 out again. 1 minus cosine theta times derivative of sine is cosine, plus sine of theta times derivative of the first term there is 0 plus sine theta. Again, distribute and then try to factor as much as we can. When I distribute cosine there, I see cosine theta minus cosine squared theta plus sine squared theta to set equal to 0, and solve will give me, again, horizontal tangents in this case. Horizontal tangents. Okay. Now, that sine squared theta, I have sine squared theta minus cosine squared theta. And that's not exactly that 1. That's not exactly our Pythagorean identity. But what I kind of see here are 2 different powers of cosine. So if I can create some quadratic out of this that I can factor, that'll help me out a bit. So I want to replace that sine squared with cosine squared if I can. So I write down sine squared is equal to 1 minus cosine squared. And then I notice that I can combine, right? I have in brackets here 1 plus cosine theta, the first power of cosine there just by itself, and then I have 2 squared powers of cosine. Okay, so what I get from this, I see kind of a quadratic there. It's just a little bit backwards from the way I like to see it, and I can switch things around. If I factor out a minus 1, that leaves me with 2 cosine squared theta minus cosine theta minus 1. And that does indeed factor. I can break that down to 2 cosine theta times cosine theta, and minus 1 plus 1 there should give me what I want. If you think about this with just x's instead, I get 2x squared minus x minus 1. That's really kind of what I'm thinking about in my head here. And when I factor that, I see 2x plus 1 times x minus 1. And now that I have that factored, when I set it equal to 0, I can solve rather quickly. Okay, so that factored form there, I set equal to 0. And again, that means I can set each factor equal to 0. So the first one, 2 cosine theta plus 1 equals 0, is the same as saying cosine theta equals minus a half. Okay, cosine of theta is a half, again, at my pi over 3 angles, but when it's negative is in the second and third quadrant. So pi over 3 angle in the second quadrant should be 2 pi over 3, and in the fourth quadrant, in the third quadrant, 4 pi over 3. Those 2 angles are the solutions to that term equal to 0, the first term equal to 0. The next, cosine theta minus 1, I can solve by adding 1 to both sides. When is cosine theta equal to 1? Well, that's only at 0. Okay, cosine of 0 is 1. So these three theta values, these three angles, provide me with horizontal tangents. And again, I want to try to find the corresponding r value. I want to write the polar points. So I plug each of these theta values into r to find the r value. We already did theta equals 0. That's at the 0, 0 point. When theta is 2 pi over 3, I plug that in. 2 times 1 minus cosine of 2 pi over 3, that's a minus a half. So minus 1 minus a minus half is 3 halves, times 2 is 3 for the radial distance, and the angle there is 2 pi over 3. And I really do see a very similar thing again here, because cosine of 4 pi over 3 is also minus a half. So I see 1 plus a half, 3 halves, again giving me a 3 for my r value. Those 3 points are where I will have horizontal tangent lines. Okay, I'll graph this for you in Desmos. And what I see here is, that's spelled incorrectly. What I see here is my curve. I see my curve in red, and some of the points there are plotted. I have the blue points showing horizontal tangent lines, and the green points showing vertical tangent lines. Okay, and I'll post this link for you in the description and at of the video here, so you can click that Desmos link and explore it a little bit on your own, and just kind of see exactly what's going on. But everything over there on the left-hand side, I've used to plot those points. You see V and H correspond to vertical points of tangency and horizontal points. And those are the angles that we found, all right? Okay, this shape here, you saw at the beginning, I erased it because I spelled it wrong. This is referred to as a cardioid. Cardioid. Because of course it looks a little bit like a cartoon heart if I were to draw a cartoon heart. Okay, thank you for watching.